Hi, everyone. Welcome and thank you for joining us today. I'm Angela Bliss, a co-lead of the Sea Ice Community of Practice on IARPIC, along with Ignatius Rigger, Nathan Kurtz, Elaine Rung, Maddie Smith, and Jingha Ding. Today's meeting topic is on the state of sea ice forecasting, and the goal of this meeting is to share recent advances in sea ice prediction and the current state of seasonal sea ice forecasting with the sea ice community. The meeting will feature talks about the GEOS S2S system version 3 and an assessment of seasonal sea ice forecasting from the Sea Ice Outlook community, as well as discussion on the future outlook for sea ice prediction. This meeting supports deliverables of the Arctic Research Plan's monitoring, observing, modeling, and prediction research goal, including MOMP 3.1, which supports participation of U.S. researchers in international Arctic modeling and prediction efforts in order to improve predictive capabilities of Arctic models. So our first speaker today is Richard Cullather from the Earth System Science Interdisciplinary Center at the University of Maryland College Park and the Global Modeling and Assimilation Office at NASA's Goddard Space Flight Center. So Richard, I'll pass it over to you. Richard's talk is titled Predicted Arctic Sea Ice Cover in the GEOS S2S System version 3.
Okay, thanks. Can you hear me?
Yes,
And can you see my slide?
everything looks good.
Okay, so thanks for allowing me to present. This is our new S2S system that I'm going to talk about. So I'm essentially going to introduce our new system and some of the novelties that are associated with it. I'd like to thank my co-authors. We have a new hire who's going to be focused on sea ice. That's Yongfei Zhang. And also, I'd like to thank the rest of the GMAO S2S team. We have a very large team that looks at various aspects of seasonal prediction. So just to give a general overview, sea ice extent is a significant climate variable, as perhaps most of the people attending here know about. It's also a key indicator of Arctic conditions. And there is also an expectation of increased human activities in the Arctic in the future. And with that increase in human activities, there's going to be an increase in a need for forecasts and a need for planning on various timescales, including seasonal timescales. And so there is, a utilitarian need for improved forecasts of sea ice. Seasonal predictions of sea ice cover have been going on for several years now. They are important for assessing our understanding and of the associated physical processes, and also our capabilities for prediction, um, and also for as I said, for planning for various human activities in the Arctic. So many centers have and continue to provide routine seasonal forecasts for sea ice, for Arctic sea ice, and many methods continue to be explored. So this is kind of a history of the GMAO system. So we've been participating, I think, since around 2013 in the ARCA Sea Ice Outlook. So our seasonal prediction system began around 2011. And so this was a main focus of Michelle Renneker. The goal was to utilize NASA space remote sensing observations for seasonal prediction, to leverage those observations for improving seasonal predictions of various phenomena. So we are now on our third version of our S2S system. So I would say that we are an irregular participant in the Sea Ice Outlook. Part of that has to do with the fact that evaluation of our operational systems has suggested that they're probably not the best for producing sea ice. Version 1, which we simply made use of because it was there and I had heard about a sea ice outlook, and I decided to submit a sea ice outlook prediction, lost most of its ice during the later part of the summer. So it wasn't a very good predictor. So we would submit primarily for the early part of the sea ice outlook prediction cycle. Then we got to version 2. Version 2 also had some issues with initialization. So we began to look at offline versions of our seasonal prediction system and its initialization. So one of the things we did was we collaborated with Nathan Kurtz in the cryosphere lab, and we tried to insert cryosphere to sea ice thickness into our initialization. It had some mixed results. And most recently, we've been using an offline version, a nascent version of our version 3 forecasting system, but without the hindcast to tune or correct our predictions. So occasionally we've been close to the observed value. Many times we have not been close to the observed value. We did not participate last year. Essentially, we had too much going on with getting this seasonal forecasting system ready, in addition to running the operational seasonal forecasting system. So we didn't have the bandwidth to participate last year. Okay. So the sea ice configuration. So for version 3, so this would be version 3, is we use a half-degree atmospheric model. This is our GEOS model. It's now version 9. So it has many improvements over previous versions. Those are mainly associated with lower level convection and atmospheric moisture processes. So we represent many physical processes in our model. We have realistic representations of ice sheet runoff for freshwater sources. We use go-kart interactive aerosols, and we have a very high top to our model. So we look at stratospheric circulation and its impact on seasonal prediction as well. The ocean model that we use for this is MOM5. We now use it at 1/4 grid resolution. It's on a tripolar grid. So this is obviously not the Arctic here, but I have a few figures of the North Atlantic showing version 1, which had an ocean resolution of 1 degree, version 2, which had a resolution of 0.5 degree, and version 3, which had a resolution of 1/4 degree. So you can see as we get into version 3, we're now really strongly into the eddy permitting realm here, and we're getting much better agreement to finer detail observations. This is the Oscar ocean current analysis that we're comparing to, and you can see that the version 3 system has a much better fidelity in resolving various aspects of the Gulf Stream current. So for our assimilation, this is probably the delay that we've had in releasing version 3, is we've had a lot of difficulty with our getting a good atmospheric circulation to correspond to our model results. So we use a in-house 3D VAR modern atmospheric data assimilation system. So this is kind of the precursor to what will be MERA 21C. MERA 21C is a global atmospheric reanalysis that we'll be releasing, I believe, next year. So that will be using our enhanced data assimilation capabilities. It will use a hybrid ensemble 4D variational data assimilation. So this is kind of the atmospheric analysis that we've used here is kind of the pre-sweeper to that. It's a 3D VAR data assimilation system, but using the modern model. In the ocean, we use a 5-day predictor corrector window for using LETKF data assimilation. So we assimilate all manner of ocean observations, but not underneath the sea ice cover. We do assimilate also satellite altimetry data as well. For sea ice, we use a continuous nudging to prescribe sea ice concentration. So that's different than our version 2 system, which only nudged on the 5-day window. So now we have a continuous nudging to the data set of sea ice that we use. So we have essentially 3 realms to our hindcasts. The very early period, which is kind of a marginal period for us, we used Reynolds, sea ice, and SST. This was to match with our atmospheric forcing. So this This 3D VAR atmospheric reanalyses is only for the 21st century. It goes from 1998 to the present. So we used MERA 2 prior to that, which was forced with Reynolds, sea ice, and SST. After that, we switched to Ostia reanalysis for the period up through 2006, and then we used the Ostia near real time thereafter. So Ostia is the UK Met Office ocean analysis. They also blend it with the OSI SAF sea ice. So there are various products that are used for the OSI SAF, and in the near real-time system, they use this near real-time OSI 401. Okay, so this is some figures associated with the ODAS here. So again, this is a comparison of September sea ice extent for the Arctic with the NSIDC sea ice index. So here we have the version 3 ODAS that we're using in lighter blue. And that's showing an offset that's due to differences in the land surface mask that's associated with the ocean model that we're using. But we note that there's a difference in the bias here that occurs going from Reynolds to the Ostia period. So it's probably likely that we will not use the Reynolds era period, or we will discourage use of the Reynolds era period for most analyses, unless a 30-year hindcast averaging period is required. I think a 20-year hindcasting average period is probably more favored for our system. The bottom figure shows a comparison of our sea ice thickness from the ODAS system poleward of 70 degrees north in comparison to various sea ice volume data sets that are available out there. So in general, our ODAS system produces a average sea ice thickness that is a bit lower than observation for the summertime period. We seem to match a little bit better for the wintertime period, although there's quite a bit of variability between all of these observed systems as well. So we're generally on the low end, but again, there's a lot of uncertainty associated with the observations of sea ice thickness. Okay, and so on the right here, just again, talking about the ODAS system, I have the analysis of sea ice concentration for a particular date in August. So the figure on the top left here is the Ostia sea ice concentration. And so that is showing yeah, that's showing the spatial distribution that our ODAS system would nudge to. The figure on the right is the resulting sea ice. So this is the blending between the model sea ice concentration and the observed sea ice concentration. So there is a characteristic difference between these two, and that is to have more ice in the Beaufort Sea and the Chukchi Sea and less ice in the central Arctic Ocean and towards the Atlantic side. So this nudging takes into account an uncertainty characterization for the observed sea ice, which is generally an upside down U shape where you have more confidence in concentration values that are either close to 0 or close to 1, and less confidence in values in the middle. And so this is kind of the resulting pattern that that you get from that kind of blending, which is kind of intriguing. I don't think we fully understood this until it finally came out of the system, but that is the differences that we have. So we're kind of interested in how these differences, particularly in the Beaufort Sea in the late summer, are affecting our predictions. Obviously, they might be having some type of impact in the Beaufort Sea in those locations. Okay, so one of the novelties of our new system is the forecast ensemble. So we have a staggered initialization. I don't think that's unusual for dynamical contributors to the sea ice outlook, that you have a staggering of the initialization date. So in this figure that I show on the right, we have a forecast that is launched on August 1st. So every 5 days through the prior month, the month of July, we release or we initialize forecasts, five forecast members on a 5-day cycle. So the axis of interest here is on the right, the ensemble count in the pale blue line. So you can see that every 5 days we launch an additional 5 ensemble members. And then at the end of the month, we launch a burst of 15 ensemble members that are perturbed in both the atmosphere and the ocean. And then we let these go then for the subseasonal time period. So this number depends on the length of the month, but it could be between 35 and 45 ensemble members that integrate. So after 2 months, which is the subseasonal period, we reduce the number of ensemble members. So we do this by characterizing the ensembles that ran through the 2-month period, and we identify strata in those forecasts, which are based on global characteristics. So they are reduced into a group of strata, and then a subset of the 40 ensemble members is then allowed to continue through to the seasonal forecast period out to 9 months. So of course, the goal of this is to reduce the overhead in integrating this number of ensemble members out to 9 months. We were particularly keen in increasing the number of ensembles that we use for our forecasts. Generally, in previous systems, we've only had like, 10 or so at most ensemble members in our forecasts. And we really wanted to increase the number of ensemble members to better characterize our uncertainty in our forecasts. So but to remove the overhead of having that number of ensemble members go out to 9 months, we wanted to reduce the number of ensemble members after a subseasonal time period. And our analysis seems to indicate that there's no unusual kink or something like that that occurs after the 2-month period, going from 40 ensemble members to 10 ensemble members. That seems to be the case. So it seems like it's working as expected. So this is the forecast that we submitted to the Sea Ice Outlook. So I've colored these ensemble members based on the date that they were initialized, going from purple out to red. So you can see in the the initialization month period here, we start with the purple, and then various ensembles are initialized out to the beginning of the forecast, which is on June 1st. And then we run for 2 months, and then those forecasts are then subset down to 10, which continue on to the remainder of the forecast period. So one of the things that we noted is that for this particular forecast, there was kind of a distribution in when the forecasts were initialized. The later forecasts in red tend to have larger values that of ice concentration or ice extent as compared to the forecasts that were launched earlier, which is kind of intriguing. So I have a $1 bet with Yang Fei about which of these groups would probably validate more. I did a little bit of analysis on this, and it suggests that the forecasts that are launched later in the month tend to have a slightly better forecast skill than those launched earlier in the initialization period. However, the full ensemble tends to have more skill than either subset. So it is important to look at the full ensemble. But nevertheless, that's also an intriguing question about this staggered initialization. So the figure on the right shows our September sea ice forecast based on the June 1st initialization. So we have a pretty close correspondence with the NSIDC values after they are corrected to NSIDC. there are some particular standouts here. The very low ice extent years in 2007, 2012 are not well represented by our forecasts. I have seen this in other forecasting systems, and so that's a curious issue. Perhaps there are phenomena associated with these events, such as atmospheric forcing, that may not be well represented by seasonal forecasting systems, or that we're missing something here associated with these forecasts. The red line here shows our forecast for the present sea ice outlook. So we are predicting low sea ice extent for this period. And as I said here, each of these ensembles, this is before they are corrected, but they do show low ice extent. So the later forecasts show a more muted anomaly, but they are still low. In the dotted line here, I show the ensemble standard deviation for each year. So one of the things to note is that the ensemble standard deviation usually is largest in the year after a low sea ice extent. So that is probably due to the fact that there is low ice in the subsequent winter, and this perhaps creates more uncertainty than in the following sea ice forecast year, that there is less ice that is more mobile, that creates more uncertainty in the forecast. I note that for the present forecast, the ensemble standard deviation is also very large, which also suggests that there's more uncertainty due to the present forecast. So this is also for 2025. I show the ensemble mean and the standard deviation and an anomaly. I wanted to just focus in on the center figure here, which shows the ensemble standard deviation is largest around the edge of the ice. You do normally see that, but not as much on the Atlantic side. So this year has the larger uncertainty. It appears to be characterized by more uncertainty on the Atlantic side than in other years. This is a look at the subseasonal forecasting time period here. So what is plotted here is the initialization date beginning for January 1st, February 20th, etc. So these forecasts for the subseasonal period are launched every 5 days throughout the year. And I've produced just a straight correlation with our ODAS for the period 2001 and 2020. So we'd like to do more analysis and assessment of the subseasonal time period. It's a lot of data, so it takes a while. I think some characteristics you can see here are this gradient going from the springtime into the summertime period. This is perhaps characteristic of the spring predictability barrier, and that's what's going on here. The other thing of interest here is this loss of predictability in forecasts which are launched in like November or early December period. There seems to be a characteristic loss in predictability that we are kind of interested in. And there's also a less predictability for the January period as well. Okay, so I've computed several statistics for comparison for our forecast skill based on our hindcast from 1998 to 2024. However, these are not apples to apples comparisons. The Pan-Arctic anomaly correlation and the detrended anomaly correlation that are shown by Mitch use a trend window, a special computation then, I believe, of the anomaly. So I believe these are not exactly apple-to-apple comparisons. We only decided on the time period here recently, and so these were the figures that I had. But I think you can generally see that with the increased number of ensemble members, we are getting a better forecast skill with our system. Even for the detrended, we go up to around 0.9 or so. So we think we're doing better. And that you can see in these figures from Mitch that the cyan colored curve is our version 2, which was not very good and it had very low skill scores. So I think this generally shows that we're doing well and perhaps up among some of the better forecasting systems that are out there. So looking at the various regions, I think one thing to note here is that we have done some comparisons with forecast skills from other systems. We seem to have a slightly better forecast skill for the Siberian region as compared to the Alaskan region for various for other forecasting systems. So that's kind of an intriguing result that we'd like to look into further, that we seem to have more skill on the Eurasian side than we do on the Alaskan side. So in the Atlantic, we tend to have lower forecasting skill than for other regions. But if you use the detrended anomaly calculation that is suggested by Mitch's paper, these values are actually larger, and you do get a bit more, you do compare a bit more favorably in comparison to other systems. Okay, so here I hope I've presented an introduction to our new forecasting system. It has some novelties and some innovation with regards to the atmospheric model, its spatial resolution. We are now down to 1/4 degree, and our ensemble, very large ensemble size, and our subsetting scheme. We have a good representation of the sea ice climatology. For the model, the free running model, there is some amplification of the seasonal cycle, but in general, it looks really, the free running model looks really good. The ODAS system has some characteristic summertime differences with other sea ice data sets. It has higher concentrations in the Beaufort and Chukchi Seas and lower concentrations in the Central Arctic. So we still have a few issues perhaps with initialization that we would like to look at a bit further. And so our subsetting scheme appears to work as suggested. So in addition to this continued evaluation, we'd like to focus a bit more on the subseasonal forecasting period, since we now have this huge number of hindcast subseasonal forecasts. We'd like to better characterize how we're doing regionally and spatially, and in other aspects for our subseasonal forecasting system. So our future S2S work will utilize what's known as the JEDI framework, which is a multi-agency system for data assimilation. So we hope to do things such as incorporate observed sea ice thickness into our data assimilation scheme. And with that, I will stop.
Yeah, thank you, Richard. That was a great talk. I think we have time for one quick question. You're welcome to raise your hand, unmute and ask, or put it in the chat. All right, we'll have more time for questions at the end, but I'd like to welcome our next speaker, Mitch Bushuk from NOAA's Geophysical Fluid Dynamic Laboratory. And his talk today will be titled Seasonal Arctic Sea Ice Prediction, How Are We Doing as a Community? Looks good, Mitch.
Great. Thanks so much, Angela. And thanks everyone for being here. And thanks, Richard, for the nice introduction. It's great to see the skill you're getting in that new system. It's really great. So today in this talk, first of all, I'll try to wrap up by hopefully 12:50 or so we have time for questions. But I'm going to zoom out a little bit from Richard's talk and do more of a sort of a higher level view of how we're doing as a community in terms of this question of seasonal Arctic sea ice prediction. And so the work I'm going to present today is a summary of this BAMS paper we wrote last year, which is really in collaboration with essentially most of the Sea Ice Outlook community. So you can see a big list of co-authors here. I want to say a big thanks to all of them, and it was really a team effort, a community effort, and I'm really proud of what we produced in the end. Okay, so just to sort of set the stage here, here's a beautiful video of daily sea ice concentration observations. And so for the seasonal sea ice prediction problem, we're trying to initialize a forecast from, a data assimilation system, as Richard described, and then make a prediction 1 to 12 months in advance, typically. And you can see in these beautiful animations that, there's a lot of variability on small space scales as well as large space scales, and also on different time scales as well. And so the predictability problem comes down to this competition between this unpredictable so-called noise that mostly comes from the atmosphere versus the predictable parts of the system that primarily come from the ocean, sea ice thickness, and the land surface. So as we know, we've seen this big decline in Arctic sea ice extent, and there's a lot of interest in our community to predict these interannual fluctuations in sea ice, as Richard introduced nicely already. And so the sea ice outlook was really born coming out of the 2007 minimum, which really caught the sea ice community off guard at the time. And this motivated the community to ask the question of whether or not we could have anticipated this record-setting minimum in advance or not. And so that led to the creation of the Sea Ice Outlook, which is a community forecasting exercise that collects predictions of September Arctic sea ice, initialized each summer on June 1st, July 1st, August 1st, and September 1st. And the SIO has now been collecting Arctic predictions continuously from 2008 to 2024. So we now have this nice 17-year record of real-time predictions. We typically get about 30 predictions each month from groups all over the world. And crucially, I want to note that this work has been funded by a wide range of agencies within the US and the UK, namely NSF, NOAA, DOE, ONR, and NERC. So here's a typical submission that we get to the Sea Ice Outlook. So this is what we received last year in June. Um, the green bars here are the submissions from dynamical models. So these are systems similar to what Richard just described, coupled dynamical models initialized from data assimilation and then run forward typically as ensembles. The red bars here show empirical or statistical methods. And so these are methods that use observational data typically to train relationships between various predictors and September sea ice extent, and then use those relationships to predict future sea ice. And then the blue bars show these so-called heuristic methods. These are less rigorous methods that are basically educated guesses, I would say. And then the nice thing about this is we can make these truly legitimate predictions in June, and then we can look at what the observations come in as. And so here's what the observations came in at last year for 2024, shown in the black line here. And what we see is that there's some systems that look pretty good, that are quite close to the observations. There's also a number of systems that have these notable positive and negative errors. So seeing this spread in predictions, a natural question is, do we expect sea ice to be predictable on this timescale? And regarding this question, there's a tension that exists in the sea ice prediction literature. So on one side, there's a number of studies that have looked at past submissions to the September Sea Ice Outlook. And so as an example, that this plot on the left here is showing the median's submitted prediction for the July Sea Ice Outlook in these orange squares. The blue dots show the observed sea ice extent. And you can just see by eye that these predictions do not look very good. So most of these papers has a sentence in it along the lines of, evaluation of these forecasts has revealed that regardless of method, forecasts struggle when the observed sea ice extent minima depart strongly from the linear trend. In other words, the forecasts aren't really adding much value beyond just a basic linear trend prediction. On the other hand, there's a whole host of studies that have evaluated individual forecast systems, and these studies have found that these individual systems, like Richard just showed, do have skill. And so most of these papers has a sentence in it along the lines of, for most predicted months and lead times, trend-independent forecast skill exceeds that of an anomaly persistence forecast. In other words, these systems do have skill relative to a reference forecast. So the Sea Ice Outlook contributors got together for a forum back in January 2021, and we talked about a lot of different things in this forum, but one kind of burning issue that came up over and over again was the need to carefully quantify where we were at as a community in terms of the skill or lack thereof of various systems. And so what that led to was making the following retrospective prediction data request to the Sea Ice Outlook community. And so what we did is we requested retrospective seasonal predictions of September monthly mean Pan-Arctic sea ice extent, regional sea ice extent in 4 regions, local sea ice concentration predictions, and then when applicable, the initial conditions and ensemble data. We requested these predictions on the Sea Ice Outlook initialization dates of June 1st, July 1st, August 1st, and September 1st, and over a minimum reforecast period of 2001 to 2020, and also metadata describing the design of each forecast system. And we received a really overwhelming response from the community. And so we got data back from 17 dynamical models, 17 statistical models, and 1 heuristic prediction. And these contributions came from 11 countries across Europe, Asia, and North America, and totaled nearly 3,000 independent predictions of September Panarctic sea ice extent. And then subsequently, we've formatted all data into a common format, which you can download from Zenodo here. And we also have all the code available to analyze and also make the figures in the paper. This data set represents the most comprehensive data set of multi-model sea ice predictions that's been assembled to date. And I encourage you to download it, analyze it, play with it, compare it to your system. It's a very fun data set to look at. Just a couple quick words on initialization. So the dynamical models, most of them assimilate sea ice concentration to produce their initial conditions. Two of them also assimilate sea ice thickness. On the ocean side, most systems assimilate sea surface temperature as well as TS profiles in the ocean. And most systems also include an atmospheric constraint, typically coming from reanalysis data. In terms of data assimilation, there's a whole variety of different methods used, including different varieties of ensemble Kalman filters, 3D VAR, 4D VAR, nudging, and forced ice ocean runs. And then these statistical models generally include some sort of sea ice predictor, whether that be concentration, extent, thickness, or velocity. And then a number of systems also include oceanic predictors and atmospheric predictors as well. In terms of methodologies, most of the dynamical models are coupled global dynamical models initialized from observations. There's also a few regional models as well. And then there's a whole fascinating variety of different empirical statistical models that are used. Some of them are fairly simple, such as linear regression or multiple linear regression techniques. And then there's a number of sort of more complex methods, such as various machine learning techniques. Okay, so let's dive into some results here. So I showed this plot on the left already, and now I'm going to show the analogous plot, but for the retrospective seasonal predictions that were submitted to the intercomparison. So the black line shows the observations. The red line shows the multi-model median, and then the shading shows the interquartile range, or middle 50% of predictions. And what you can see is that the multi-model median prediction looks very good. It's capturing the trend in sea ice with high fidelity. It's also crucially capturing many of the interannual fluctuations we see in sea ice, including to some degree the 2012 and 2007 minima, although it's not capturing the full magnitude of those anomalies. We wouldn't necessarily expect it to from July 1st is a key point, I think. And then in terms of skill metrics, we can quantify skill, as Richard said, using the anomaly correlation coefficient, or ACC. That value is very high, quite close to 1. A more stringent metric is this detrended ACC, where we first remove the linear trend from both the observed and predicted time series, and then compute the correlation. That value is also above 0.8. So quite a bit of skill at predicting these anomalies relative to the trend line. Okay, so now we can get a bit more rigorous, and we can compare our skill to some reference forecasts. So I'm going to show two reference forecasts here. The dashed gray line shows a linear trend climatology. This is simply a linear trend prediction based on all available past data. And if we look at ACC, we can see that the trend climatology has an ACC of around 0.7. So that's telling us that half the variance of the observed time series can be explained by purely the linear trend. And then if you allow yourself to also add to that linear trend climatology a damped anomaly, we can get the damp persistence forecast. And what we see is that by doing that, we get the solid gray line, and we can add quite a bit of skill, especially from September 1st and August 1st. And so this damped anomaly persistence forecast is shown over here. And so to get that, you basically take the observed anomaly at the initialization time, and then you scale that by the observed autocorrelation, and then also a factor involving the variance of those anomalies. Okay, so now we can add the multi-model median prediction skill to this plot. And what we see is that the multi-model median is clearly beating damp persistence for both ACC as well as detrended ACC at these sea ice outlook lead times. And it's essentially tied with damp persistence from September 1st because the damp persistence prediction is very good from September 1st. Okay, so now we can make this a lot more complicated, and we can add the 17 dynamical models onto this plot. Richard already showed this quickly in his talk as well. And what we see is that as a whole, the models do have some degree of skill. And so if we compare to damp persistence to start with, what we see is that from June 1st and July 1st, most models are beating damp persistence. From August 1st, it's about a 50-50 split. And then from September 1st, most models are actually losing to damp persistence, which is suggesting that they're probably making some errors in their initial conditions. There's quite a degree of skill spread across the various models, but there are a number of models that have detrended ACC, for example, above 0.6 at these CIS outlook lead times. So these are what I would call, potentially useful forecasts. There's also one model that kind of stands out above the rest, which is the solid gold line here, which is the ECMWF CS5 system, and it's doing quite a bit better than the other systems. I think Richards would have fit in somewhere around this dash red line. It looked like in his talk, I think. Here's the same plot now for the 17 statistical models that's submitted to the CIS Outlook. Again, we see quite a bit of spread across the various models, but we do see a large group of models that are beating damp persistence quite convincingly, especially at these longer lead times. And again, we see a couple models that are sort of positive outlier models, the green line and the orange line, which are the AVI model, which is kind of a multilinear regression technique, and the COPRI model, which is a machine learning technique. Okay, so people often ask the question, are dynamical models or statistical models better? Oh, sorry. Is there a question there? Maybe not. Yeah. People often ask the question of, are dynamical models or statistical models better at predicting Arctic sea ice? And I would say in this comparison, it's hard to make a definitive statement on that question. There's a large spread across both groups of models. There are models with very high skill in both groups. But I will say, I'm not going to show it here, but if you go down to the regional scale or also the local scale for sea ice concentration, the dynamical models do start to win more convincingly over the statistical models. And that's possibly because they're starting to represent more of the dynamics of the system in a faithful way. Okay, so we can also ask the question of, is sea ice predictability changing over time? It's been suggested that as the Arctic thins and the ice becomes more mobile, it's going to be more susceptible to unpredictable atmospheric forcing. And so what we can look at here are the sea ice the sea ice extent absolute errors plotted as a function of time along the x-axis. And then each color shows different initialization times going from September 1st back to June 1st. And so what we see is that as we go to shorter shorter lead times, we get lower errors, as you'd expect. And then in terms of trends, I would argue that these time series do not show a clear trend. Rather, these look fairly flat to me, but rather they're punctuated by a few years that have very large errors, namely 1996, 2007, and 2012. And these are well known to us in the sea ice community as extreme high, low, and low sea ice extent years. And there's been this kind of notion in the sea ice predictability literature that the systems really failed in these years, in the sense that they had very large errors at capturing these 2007 and 2012 anomalies. But I think an important point to make here is that the gray line here shows the error made by a linear trend prediction in those same years. And so we can look at this a bit differently, and we can look at the error improvement relative to that trend climatology prediction, where here anything positive would indicate an error reduction, anything negative would indicate an error degradation. And what we see is that it's precisely those extreme years, 96 to some degree, but especially 2007 and 2012, where you get a very large improvement relative to the linear trend prediction. And so it's actually precisely these extreme sea ice years where you get the most added value from the prediction systems, and you would most want the prediction systems in these years. So I would counter the literature, and I would say it's actually not fair to say the systems failed in 2007 and 2012. These are actually, in some sense, their biggest wins. Okay, and I'll just quickly wrap up with some system design comments. So we also did some analysis of grouping the systems based on various system design aspects. And so here are some different design aspects of the dynamical prediction systems. And so we grouped the models.
What was that?
Oh, sorry. Sarah.
Come on, wake up, you.
Okay.
Both of you guys, get up. Don't go back to sleep.
So the red line shows the models that assimilate sea ice concentration and SST respectively. The blue line is the models that don't assimilate those variables. And what we see is that assimilation of SIC and SST help the September 1st prediction substantially, but then for these longer lead times, they don't add that much skill. Panel C shows the influence of ice ocean resolution, and here we do see quite a clear separation, where the models that are run at higher ice ocean resolution appear to have clearly higher skill at all of the sea ice outlook initialization times. This is quite an interesting result, I think. And then panel D shows the same thing, but for higher atmospheric resolution models. There's what appears to be a small benefit from running at higher atmospheric resolution, but that benefit is not significant with this set of models. Here's some similar plots for the statistical models that's submitted. And here we found an interesting result that the models that include oceanic and atmospheric predictors shown in red here actually have lower skill than those that do not. And what we think is going on here is we know, of course, physically the ocean and the atmosphere do influence the sea ice, so those predictors should help you make a better prediction. We suspect that these systems may have been a victim to overfitting, and possibly they've overfit to the past record, and then they aren't generalizing well when you predict the future. So likely with some better training techniques, you could probably remedy this gap quite a bit. And then panel C shows the influence of machine learning methods versus not. And what we find is that the ML methods do not have a clear advantage, at least in a multi-model sense, over the non-machine learning methods. But there is at least one ML method, the Copri model, which is extremely skillful. Okay, and now I just want to quickly return back to this tension I kind of started the talk with. And just to remind you that the tension was the fact that the real-time predictions submitted to the Sea Ice Outlook have much lower skill than these retrospective seasonal forecasts that have been done. And so why is that? So in the paper, we have a long discussion on this, but we think the leading order reason for it is basically a model selection bias. And so I'll explain that over here on the right. So the red line shows the multi-model median of the retrospective forecasts that were submitted to the intercomparison. The blue line shows the multi-model median submitted in real time to the Sea Ice Outlook. And what we see is that over the years 2008 to about 2014 or so, there's a large gap between those two, but then they fall much more into line between 2015 and the present. And if you look on the left here, this is showing the submissions by various type to the Sea Ice Outlook over time. And what we found is that in those earlier years, first of all, there weren't that many submissions coming in. A fairly sizable fraction of those submissions were shown in green here were these so-called heuristic submissions, which are basically educated guesses, not very rigorous. Also, the blue line shows the dynamical models. There weren't many models submitting, and those that were submitting were just, as Richard said already, we're basically figuring out how the heck to do sea ice predictions. They weren't very sophisticated yet, and they were just in their absolute infancy. So we think the simple reason for this skill gap in the literature is just that the submissions were done with fairly immature systems over the first 7 years or so of the Sea Ice Outlook. And then after about 2015, the systems did get better. And we expect that as we run more and more into the future, this gap between retrospective and real-time predictions should be closing quite substantially. Great. So I will quickly wrap up. I'm not going to read my conclusions here because I just said them. But if you want more details on the paper, you can scan this QR code and read our paper in BAMS. And then I just want to finish off with one really crucial point, which relates to funding. So the Sea Ice Outlook does not have funding at the moment for the 2025 season. We are running a Sea Ice Outlook still. There's an active call out right now, and a number of folks have submitted predictions for 2025. But we don't have funding yet. We thought we had some lined up, but it's fallen through due to all the uncertainty right now regarding climate science funding from NOAA. So obtaining funding is really crucial to sustain this record of real-time predictions. Because there is this gap between real-time and retrospective skill, we think keeping these real-time predictions going is really important for us. And also to sustain this amazing community of international collaborators who have galvanized around this problem of sea ice predictability. So with that, I will wrap up, and I'm happy to take any questions or thoughts you might have.
Thank you, Mitch. That was a great talk. I'd like to open it up to questions for Mitch, and then also we'll have time for questions for Richard too, as well as discussion.
Hi, this is Rosemary Atongarok and Noxit. When we're looking at these variables, and you can see that we're having differences various years, like here in Noxit, we had some really very cold weather last year, and it was really different. And then this year we're later than the last few years for breakup. Um, for me, it really is important because of the amount of ice road creations that we're having and the various drainages that may be affected by this. Is there ways that we can look at um, a broad view, overlaying some of these things that might be contributing to flooding events that we're having?
Yeah, thanks so much for that question. So I think you raised a really key point, which is that everything I talked about today and also in Richard's talk primarily, we were mostly looking at this Pan-Arctic sea ice extent number, which is a useful number for kind of summarizing the general behavior of the whole system, but for any individual user of the forecast, that's going to be completely useless. So in our paper, we did do some analysis on sea ice concentration predictions, which would be sort of, predictions evaluated at sort of a local 25 by 25 kilometer scale. And we did find that most systems had some degree of skill at those spatial scales, but the lead times are shorter over which you have that skill. So predicting, sea ice coverage, 3 months in advance at a given grid point is a fairly challenging problem, but probably if you're looking for a 4 week or maybe a 6 week prediction, we think there is some hope for that. So we think that we have reasons to believe that we can provide some useful planning, forecast for planning purposes on maybe a 0 to 6 week time scale, but um, we haven't really produced actual products that folks can use yet. And I think that's really the next step that this work has to go to is trying to move towards sort of the actual users and figuring out how we can provide the information they need. Also, these forecasts, everything I talked about today was fairly deterministic. It was just basically a number, like predicted numbers, and what users want are probabilistic statements, like the odds of it being an early or late breakup year, for example. And so we need to do a lot more of that probabilistic analysis as well.
Are there other questions for Mitch or Richard?
So Mitch, I have a question. Do you
Sure.
think, so in the future here, do you think, I think the focus is on machine learning. So do you think there will be more machine learning forecasts? And are machine learning forecasts correctly characterized as statistical methods, or should they have a catalog of their own?
Um, in my view, they are just they are statistical methods. Like they're taking past observations, learning relationships, and producing a forecast. So I view that as statistical. And some of the methods that are non-machine learning are quite complicated. Like you compute a bunch of EOFs and then you do a bunch of filtering on them and I, I don't see a clear distinction personally between ML and statistical. But I do think the ML methods do have a lot of potential for pushing the skill forward, and we've really seen that in weather forecasting. We're undergoing a revolution as we speak with ML forecasting, and I do think for sea ice, at least for certain variables, we can probably we'll be seeing the ML methods doing as well, if not beating the models pretty soon. I think for a lot of forecasting applications. Yeah. The climate problem, I think, is a harder one, but I do think for seasonal, I think the ML methods are going to do pretty well, is my feeling. If there's no other questions, I might pop one for you, Richard. I was curious
Go
with
ahead.
with the data assimilation you're doing. Is that being done component-wise individually, or is it being done in a coupled sense? Like, do you have just one DA run that does ice, ocean, atmosphere simultaneously, or are you kind of doing them offline and then putting them all together to initialize the forecast?
It's fairly complex. So I think we would characterize it as weakly coupled. So the atmospheric assimilation is done separately. And so that's all finished before we work on the ocean assimilation. So we have a predictor corrector scheme that runs on a 5-day window. So the predictor scheme incorporates the observations and essentially produces analysis 5 days forward. So then the difference with the background is then characterized as the innovation. And so you back up the model and you run it again with the innovation as an additional forcing mechanism to produce the background ODAS. So it's quite complex. So in version 2, we had corrected the sea ice concentration just essentially on the 5-day time period. And that creates a lot of blockiness in the time series and a lot of artifacts and things like that. So for this time, we've corrected the sea ice essentially continuously as the background model runs. It's corrected at every time step. And that's produced a much better assimilation. The other thing that we've worked on here is the fact that, given the fact that our previous systems essentially lose a lot of ice in the summertime, and so there was a lot of focus on preserving the ice thickness. So when you take changes in the ice concentration and apply those to the various categories in SICE, we had previously been doing that, I believe, for each of the categories, but here we've gone with a sequential effort to address the thinnest ice category and then proceed upward. So that also seems to have an improvement for our ODAS system.
Question from Lauren.
So I guess as an add-on to that, I'm wondering if you're doing map projection changes as you're aggregating some of these things in, because I just feel like polar projections are useful for sea ice, but a lot of this is not done in a polar projection.
That's right. So our system runs on an exchange grid system. So we have a different grid for the atmosphere. We have a different grid for the ocean. And so those are communicated using an exchange grid system. So for the ocean, we run on a tripolar grid with poles within Greenland and within Eurasia to avoid polar singularities in the ocean. And so we compute the extent based on that grid. So that seems to be the safest thing to do, is to simply operate in the native grid of the ocean model.
And we have one question in the chat. Has the wind combined with higher temps sped up the melting?
I can definitely take that one. So absolutely, the combination of winds and temperatures are both big contributors, and that's part of the reason this problem's hard, I think, is that the winds are largely a weather prediction problem, but there may be some predictability at the longer time scales for winds. And so the winds are kind of, you're fighting against that source of unpredictability constantly, but then the winds do imprint some signals if you kind of do it integral, like a time integral, a sort of a accumulation of the effects of the winds. Those get stored in the ice thickness, and the thickness has this thermodynamic persistence to it, and that gives you some predictability. So sort of the success of these systems kind of comes down to like that interplay between how much you're getting, how much the weather systems are messing up your predictions versus how much that encoding is able to persist through the melt season. Yeah.
And we have one last question.
Hi, Mitch. This is a question for you. Great talks, by the way. I was wondering because over time there's a larger number of submissions, and some are statistical heuristic, and especially in the last years with the machine learning and AI models. I was wondering if there was any thoughts in including some form of measure of the computational cost behind different techniques, especially we have high resolution, low resolution. And so probably with these different submissions, there's a wide different computational costs behind these predictions. So has there been any work in including that in the comparisons?
There's been no work on that. I think it's a great idea though. I think that is, in addition to being more skillful, I think that's another huge advantage of these ML or statistical techniques is that they're basically cheap to run if you can get the observations. So we have not analyzed that. I do think that that result I showed where the higher ice ocean resolution models look better. I think there could be a confounding factor in that, in the sense that the centers that can afford to run high resolution are well resourced, and they tend to have bigger teams, and they're well staffed, and they probably have more effort put in terms of developing a high quality prediction system. And so I think that that could be a confounding influence there that we're seeing with the ice ocean resolution, is it's basically a proxy for resources for a given center.
Yeah.
Yeah, so I think we need some more clean tests to actually see, run the same system at high and low res to see if it actually does help skill that much. Yeah.
Okay,
I
thanks.
could, I think our system is kind of taxing our available resources. I mean, I think the main issues are the speed of the ODAS, and I think that is a place where we could use machine learning to perhaps speed that system up a bit. The other issue, though, is the ensemble size and the amount of output. So I don't think that changes with machine learning. I've seen presentations where people talk about thousands of ensemble members using machine learning systems. So that really is a big issue for us with our dynamical system. Our system is at least a few petabytes for our hindcast, and I think it's tens of petabytes in reality. So just being able to process that amount of information will be a continuing challenge going forward.
Thanks.
All right, thank you so much. We're a few minutes over, so before we leave, I'd like to thank both of our speakers, Richard and Mitch. This was some excellent discussion today, and I really appreciate both of your presentations today. So thank you, everybody, and thank you for joining us.
Great. Thanks a lot, Angela, and thanks everybody
Thanks.
for joining. Much appreciated.
Thanks. Bye-bye.
Bye.
Thanks.